Eliana Fu from Trump coming up to the stage. So Eliana is an industry manager at Trump for their division of aerospace and medical. And she's going to be speaking to us today on green laser applications. So Eliana Fu was educated at Imperial College, University of London, with a master's and then a PhD in materials science. Eliana also performed postdoctoral research at the Loughborough University UK and Clemson University USA. After working extensively in the traditional manufacturing world, which I guess we are all familiar with TWI, then she went to TIMET and SpaceX. She then turned her attention to additive manufacturing at SpaceX, and I just think Eliana's the coolest. She's been working at SpaceX. That's awesome. And so she's been working with Relativity Space as a senior engineer as well in additive manufacturing technologies. So most recently, Eliana has joined the Trump team as an industry manager for aerospace and medical. She has served as an advisor to the LA Mayor Eric Goretti's Advanced Manufacturing Committee. She is currently the Women in 3D Printing Ambassador for Las Vegas and is also on the Technical Advisory Board of Hyperion Metals. Eliana has written a book based on her experiences as a female engineer at SpaceX. Eliana, welcome. You seem like such a full throttle expert. Yes, we can.
Okay, great.
Let's get started.
Yeah, thanks so much. And I just would like to thank Women in 3D Printing and you all for joining me. I know that some of you started your day really early this morning, like at 8 a.m. Pacific time. So it's 4:30 for me, so I've also had a long day. So thanks again for joining. My presentation is a Trump presentation, which is the best kept secret in laser additive manufacturing, green lasers, a unique innovation. And I just want to shout out my co-authors who are not on this call, but they are Roland Spiegelhalder, Sabrina Vogt, and Marco Goebel. Just so you know, Trump, who's our employer, is a technology leader in two fields. It's basically known in the industrial world as the Rolls-Royce of the laser world. It's a family-owned business, and it's been around for almost 100 years. Pretty severe-looking picture of the family there. Mr. Trump, please remember to pronounce the F, left his company to his godson, and then the godson left his company to his son and daughter. So the son and daughter are the president and CTO, and the daughter's husband is the CFO. So it's like a 14,000 person company across many different countries in the world in additive manufacturing. That has been in existence at Trump since 1999, with a little more than 250 employees supporting that sector. So it's small but mighty. I would say 75% of Trump's traditional business is the 2D laser cutting sheet metal for automotive. That's the bread and butter of the laser world. I don't work for that division. I work for laser technology, which is 3D laser cutting, welding, marking, surface structuring, and 3D printing. So that's the thing that I'm most interested in. About me, I actually come from traditional manufacturing. So until maybe 15 years ago, I didn't even know what 3D printing was. I was educated in UK, as you can probably tell from my accent. And all I knew was that material science or metallurgy was metal bashing. So it really wasn't until I was working for the titanium company, TIMET, which is one of the bigger titanium producers in North America, that more and more of my customers were asking for 3D printed products. And I was like, what's that? So I decided to find out more about that. I joined SpaceX, who was one of my customers. And then I really started getting into learning more about raw materials for 3D printing, whether that's metal powder or wire. Then I realized that all these products are made by the same people that make bulk metallic products like billet, bar, sheet, plate, ingot, and quill. And at Relativity Space, I was senior engineer for additive processes. So I not only looked at materials, I looked at supply quality, I looked at additive processes, whether it's laser powder bed fusion or laser DED or wire arc additive manufacturing or WAM. that we call at Relativity Space. And Relativity Space, just in case you are not aware, is trying to be the first company to launch a fully 3D printed rocket. So right now I'm working for Trump as industry manager for aerospace and medical. So there's two pretty interesting industry sectors that I'm interested in. I did serve some time on Mayor Eric Garcetti's Advanced Manufacturing Committee that looks into improving jobs using advanced technologies like 3D printing in the Los Angeles area. I don't live in Los Angeles anymore, so that's very sad. But I'm now in Las Vegas, and maybe I can help do the same for them. Just as a side note, I am on the technical advisory board of a company called Hyperion Metals. So just some background. I'm a strong fan of 3D printing.
Apologies, Eliana. I might just jump in. I think we're meant to be sharing slide 4. We can see the PowerPoint with the slides on the left. Would you like to just try resharing your presentation?
Oh no, what happened?
Slide 4? That's okay. We can see your screen, but I think it was just the functional view of the PowerPoint.
How about this?
Brilliant, lovely.
Okay, was it going too fast?
Now.
Can you hear me now? Is there a remote problem?
No, this is all okay. Please continue.
Okay, so I'll go through this quick. So I think everybody knows the reasons why AM is popular in aerospace, whether it's commercial or military or satellites or UAVs and drones, and particularly the thing that I'm interested in, space exploration, because I've spent a lot of my later years lately working in the space exploration area. So just on the laser AM methods that at Trump we're particularly interested in, whether that's laser powder bed or laser DED. By the way, Trump has different acronyms for that. I don't know why, but powder bed fusion, which everybody calls, Trump calls laser metal fusion, and DED, directed energy deposition, Trump calls laser metal fusion. So if you see that written anywhere, that's what those means. And each one has their pros and cons. Each one has good points and bad points, depending on what you want to build, what materials available, the size of the part, whether you're looking for fine features or controls or thin walls, or you're looking for a better surface quality, or you don't care about surface quality and you just want to get something big that's printed. Each of these things can give you whatever it is that you're looking for. So I'm going to try and concentrate talking about these two technologies today. So why is it exciting for laser AM in space? And I think we've had also some presentations from JPL and from NASA today, but there's so many different applications. And the exciting thing is 3D printing. Parts are on Mars. I mean, they're mind-blowing. They're actually on another planet. So I'm not familiar with all of these things. Some of these are sensors, some of these are cameras and so forth. But all of them are either a mix of laser powder bed printed parts or laser DED printed parts. So I think that's pretty amazing. And then whether you're talking about rocket ships or satellite components, or I've also included the barrel section of a rocket, but maybe you can put that to the side because that was actually produced by Wham. But for those highly intricate parts, or where you have a very low volume but high accuracy, and you want to basically take control of printing that part into your own hands, whether it's waveguides for antennas, or even rocket engines, so thrust chambers and things like that. All of these can be 3D printed with laser AM. And so it is an advantage for space, but why do we care about it? And I think this is something that people probably don't mention a lot, but apart from all the different advantages that we spoke about just now, honestly, for me, I think it's lead time. Cutting the lead time for metallic product, whether it's sheet or plate or whatever it is, actually allows you to make and assemble your vehicle, your rocket engine, your part, or even structural component much faster than if you waited the traditional length of time for material. I remember when I was at SpaceX and I called a different titanium company. I didn't call my former employer. I called a competitor in North America, and I just inquired for regular Ti 64 sheet metal, I think 48 inches by 96 inches long. And they told me the lead time was 52 weeks. And I had a huge laugh, because in 52 weeks, you know, at SpaceX, we would have already launched like 4 or 5 vehicles at that time. 52 weeks, you're crazy. So if you take that part of that manufacturing time back into yourself, you can actually open up more launch windows for your customers. So anybody who wants to get satellites in space, or they could be probes, or they could be things like James Webb Telescope or anything, that allows more people to have things in space, which I think elevates and escalates the amount of knowledge and information that we can share and gather from launching things into space. So, shifting back to the title of this presentation, which was the best kept secret in additive manufacturing is green lasers. Why do we even care about green lasers? So most of you who do laser AM, you're very familiar with IR lasers, because most machines, whether they're EOS machines or Trumpf machines or Renishaw machines or Concept Laser or SLM, they're all infrared laser sources which you use to melt material, and those will always be metallic, right? So that wavelength is invisible to the human eye, so it's in the higher length of the spectrum. So the wavelength is between 1060, 1063 to 1070 you've seen. But what actually is a fact is that a shorter wavelength in the visible spectrum of light could be better for other materials which are highly reflective. So those are materials like copper, aluminium, gold, platinum, iridium, silver, and palladium. Some of those are noble metals because they don't form oxides very easily. So they're very expensive because they're also used in jewelry and things like that. So at Trumpf, being the Rolls-Royce of the laser world, Trumpf have developed cutting and welding techniques with visible spectrum laser light, so laser sources in the green wavelength. And they demonstrated this very well on copper. So cutting and welding copper sheet. So the problem why you want to try and avoid doing that with IR is that you'll find that the beam has difficulty coupling to the surface of the metal. You usually get a lot of back reflection, lost energy, and a lot of spatter, which also results in poor welds and weld quality. And you can translate that to the 3D printing world. So the thought process is to combine a green laser source with a 3D printing process, whether it's laser powder bed or laser DED. So you'll have better density, lower porosity, a better surface finish, and less spatter. So you have better productivity. And this is true of all these other materials as well. So, you know, why we care, because there are certain materials that we really want to work with in 3D printing. I think a lot of people have a common misconception that you can 3D print anything, and that's actually not true. Sometimes the feedstock is not there. Sometimes the parameters are not developed. So using a tool like a green laser wavelength can help you get over some of those problems. So yeah, what are those materials and why do we care? So let's talk about copper, for example. So copper, as we know, has really good thermal conductivity, but also electrical conductivity and some corrosion resistance. So whether you're thinking about rocket engines or rocket engine parts, or even things like PCBs and circuits and things like that, transistors and things like that, all those kind of things, which could have been very difficult to print with IR lasers, can now be printed very nicely with green lasers. So I just want to show you some results that Trumpf has demonstrated. So this is LMD, which is also known as DED of copper chrome zirc. That is an alloy called C18150 in the industrial world. It's a very commonly used material. And so we have the shorter wavelength at 515 nanometers in the green on the left-hand side of the screen, with IR at 1030 nanometers on the right-hand side of the screen. And all what they've tried to do is to deposit blown powder on top of each other, so you could create layer on layer, and try to compare your results with a green laser versus an IR laser. So let's look at the left-hand side. So they've managed to build up 10 layers pretty nicely. You can see this section through on the top. There's a little bit of maybe undercutting on the side there, but on the whole, it's not too bad. And if you look at the side view, there's not too much, there is some porosity for sure, but it's not as bad. If you look at the right-hand side, which is with IR laser, you can see the side view shows you even cracking of the substrate and a huge heat affected zone. It looks like they've given up even trying to deposit after the third layer. So they didn't even make it to 10 layers. They quit after third layers and they were like, oh, it's not working out. Let's just peace out. And if you can see the bottom there, that view shows lack of fusion basically all the way through that attempted print. If you look at this view here, also trying to build up like a fillet weld, and this is also just depositing blown powder in a DED process. That top line there is using the green laser of 515 nanometers. And that bottom line is showing you the IR laser. And as you increase in laser power from 425 watts to 750 watts, so you go from the left to the right-hand side of the screen, you can see the quality of the weld deposition that you can achieve. And so what I think is pretty startling is that even though with the IR laser, you're pumping in way more power, you're not actually getting a bigger deposit. You're not actually able to deposit more material. And so that's basically due to a lot of the energy being lost. You need to pump in more energy to even get melting started. And that heat energy is also then being transferred through to the substrate, which is not cool. So what you can see is basically, if you look at the conclusion of the big arrow there, that means that 515 nanometers green wavelength has a bit more of a stable process, and that you can increase that build rate, but still have a lot more material being deposited for the same amount of power, laser power, I should say. And then finally, on this kind of cuboid, they call it a cuboid here, and they're trying to build a kind of 3D structure, but we've still got a side view here. We're comparing the green laser. Thankfully, somebody has marked it in red and green here, so it makes it easier to see. But at 515 nanometers, this is the size of the cuboid or the mass that you can deposit, versus if you look at with the IR laser, you need more than double the amount of power to get the same size cuboid. So I think that pretty much speaks for itself. You know, if you don't have to whack up the power in the laser to get the same size deposit, I think that's more effective. So just looking at some different kinds of things that we've printed here. So this is with laser powder bed fusion now. So the left-hand side is pure copper and the right-hand side is copper chrome zirc. And again, so we've just tried to do some parts or components that resemble real life industrial parts, whether they're inductors or transistors or combustion chambers for rocket engine. It's a pretty nice surface. I do not believe these are photoshopped, but they may have been bead blasted just to remove some oxide there. But that kind of happens with handling the parts. This is worst case scenario. I don't think I've ever seen anything as bad as this. And it's just comparing the porosity that you get with an IR laser. I mean, maybe this is, I don't think you'll ever see anything as bad as that, but I have seen welds with copper, which look pretty bad. And I can say that translating that to the 3D printed world makes you really want to lean towards the green wavelength for anything like copper, for example. So again, just looking at some of these parts, I think these are pretty nice. I mean, they're kind of small parts, reasonably easy to print. We also have done some initial green laser DED or LMD trials with copper. This is with actual material called GR-COP42, which is material that was developed by NASA and specifically for rocket engines. This is using an open system, green optic, and the work was done by Fraunhofer in Plymouth, Michigan. And so that's just blown powder with a robot movement there. And the idea was to try and make a couple of examples of, let's say, a racetrack so that we could extract tensile coupons, a cylinder so we could see how nicely the path planning on a robot will work, and then ultimately to make a rocket nozzle that could be hot fired. So we never actually got that far until the funding for the project ran out, which is a bit sad. But here we've got some parts that we did make, and surprisingly, very easy without a lot of parameter development, getting this kind of nice feature size, wall thickness about 1.2 millimeters, not a lot of power, so 700 watts, which I think is fine, even though we had the possibility to go to 3 kilowatts. We didn't need it. And what I found really surprising for a first attempt and really not doing a lot of parameter dev is that surface finish was good. And I was very surprised at this. So I like this one a lot. So the next piece of work for us to do is to try to find some kind of funding scheme where we can print a full rocket nozzle and have that hot fired somewhere. So that work is ongoing. That would be an example of, let's say, so this image on the bottom right here was actually printed by TWI in the UK. This is nickel, but just imagine if he could print that with copper. That will be a pretty interesting item to see, and also to have that hot fired will also let us know whether that's a sustainable or good method of manufacture that we can reproduce, you know, at any number of different vehicle launch companies. So, changing the subject completely from space to jewelry, consumer products, art, and sculpture. So, because I live in Las Vegas now, the Raiders Stadium, the Allegiant Stadium, is the brand new stadium in town. And it also, in case you haven't been there, it also houses the world's, so far, biggest 3D printed sculpture. What is actually 3D printed are the polymer blocks underneath the aluminium metal sheet that's on top. But it's meant to be a torch that's like the Olympic flame or something, but it's the torch of the Las Vegas Raiders NFL team. I'm not an American football fan, so I don't really know too much about it, but it is pretty impressive if you go up to it. So that's a pretty cool thing. So I think what we get from this is 3D printing is used like in every industry sector, including sculpture and art. And so it's not even uncommon now to see that in things like 3D printed bridge that we've seen installed in the Netherlands, and we've seen 3D printed housing in Austin, Texas. So, you know, I think that's pretty amazing. But for jewelry specifically, this is a really interesting subject matter because 3D printing allows you to do unique designs and shapes and also print in certain materials that it would be very hard to do. So for example, people always ask me, because I have a titanium background, why it is that you do not see a lot of diamond engagement rings made out of titanium. So the answer is, that material is incredibly strong compared to traditional jeweler's material like gold and silver and platinum, where the metal can still be worked by hand by a jeweler. If you 3D printed it, that's a different story. So I think if people can put their mind to using something like the power of 3D printing for jewelry, we could see a whole nother raft of applications here. And if you think about the precious metals, particularly like platinum and gold, which are expensive, I think we can also try to bring down the cost, or at least reduce waste. So those materials are very expensive. Here's a couple of examples that Trump has printed in, say, rose gold for watch cases. So these are 3D printed watch cases, and that's using laser powder bed fusion, or LMF as Trump calls it. And we got very good results with, I'm not a jewelry expert, but some of these materials like 18 karat white gold, 18 karat rose gold, some palladium alloys, and some silver alloys as well. So, you know, you can achieve a as printed density of not greater than 99.9%, which was pretty amazing. And the better finish saves on excessive post-processing, reducing waste and machining and so forth. So I think that's pretty amazing. So thanks for listening, everyone. This has been a fun and interesting presentation. I think that green lasers are the best kept secret in laser AM. You don't come across them very often, and not many of the manufacturers have the green laser optic. But if you do manage to integrate them, I think that where it's providing value or having some kind of unique benefit is in the high value precious materials. You can use them combined with AM for customization, unique shapes and designs. Whatever industry you're in, you're decreasing the lead time between the design creation and the part manufacture, and you're reducing waste and overall costs. So honestly, whether it's space exploration or high value art or jewelry, I think a green laser with any of these materials, 3D printing has a part to play. And I just want to thank all the people for providing some of the data and information for this presentation.
Wonderful. Thank you, Eliana. Really insightful presentation. Love what you shared about your journey in dabbling in the rocket space. I have a question for you, actually. So I find it really intriguing that we talk about post-processing, which is a hot topic right now. So with the green laser, just a bit of a question around how you achieve the refined surface finish with that particular laser. Do you alter some of the parameters, like let's say power, duration, on the surface in particular, to get that refined finish?
There's no difference in the parameters for achieving the surface finish. So for example, those samples that I showed you of the racetrack and the cylinder, the same parameters used throughout. So what it is a combination of layer height, those were blown powder, for example, but if it was powder bed, it would be layer height and power and speed and so forth. The same thing with blown powder, nozzle, and also the path planning of the robot. So all those things combined, you're thinking about now the molten material as it spreads and solidifies, which essentially is what metallic 3D printing is. It's like a marriage between casting and welding. That's the kind of structure you get. And so when you're not pumping in a huge amount of IR energy, you're just using what you need in the green wavelength. You're not having all these back reflections and spatter and defects and lack of fusion or unmelted particles. You're eliminating all of those things. So as the liquid metal spreads and then solidifies, you are getting a better surface because of the flow. So it's not really, in this case, it's not really, you're not really changing anything on the outside, but for a more complex part, you certainly could try that.
Thanks for that answer. So another one here, which has been upvoted. What is the largest part, product or sculpture that has been printed with the green laser?
I don't know if anyone was following me on LinkedIn 2 weeks ago. We printed a pure copper part for Josie at Hyperganic in Munich. And it was printed on the TruePrint 1000, which is 100 millimeters by 100 millimeters by 100 millimeters green in Plymouth, Michigan, and sent to me in Las Vegas, and I gave it to her at CES. So if you find a picture on LinkedIn, she is posing with that part, but it's not very big right now. For powder bed, that's about the size that we can do. There is a plan to transition the green optic to the larger TRUMPF machines, maybe 350 millimeters by 300 millimeters. But if you put that green optic freeform in any other DED system, so TRUMPF has an enclosure that they use for just cutting and welding, and that box is 4 meters long. Somebody has to do it. They haven't done it yet. I'm waiting for someone to do it. They could print a 4 meter long rocket engine.
One last question before we hand over to our next presenter. What has been your experience obtaining certification or verification for components that have been manufactured with the green laser?
Yeah, right now we haven't had anything verified for flight. So it's all been consumer products, which watches, jewelry, that kind of thing. And aerospace has only started dabbling in it right now. So if you want to hang out and talk to me in the networking or hit me up on LinkedIn, I can go into that in more detail. But I think the next participant is up.